Okay, folks, we talked about the other day. I showed you this was probably Thursday last week. Demonstrated what f plus g of x, what we were doing with that, what it looked like graphically. And what we mean by this is that we're going to take f of x and add to it g of x. Well, remember what f is. F of x, this is notation for a y value. Okay? It's the y value that is on this red curve for whatever x value I choose. Does that make sense? This value here is also a y value, but it's off of this blue curve. Okay? So what we do, and you can see the picture over here, but I'm going to walk through this a little bit slower on this picture here. What we get is if I were to take this x value right there, that x value, okay, and I look at what is the y value for f, would you guys agree that all I need to do is I need to come up here and see where that intersection is, and it would be then that length. Does that make sense? Is that okay with everybody? That length right there is f of x. Okay, that's the y value for the red function at that x value. Okay? Then I'm going to do the same thing for g of x. Okay? At the same x value. So I'm going to come up. I'm going to see at that x value, where does it intersect the blue function? So it'd be at that point right there. Okay? That is going to then establish, I'll do it in blue here. That's going to establish that length right there. Okay? So we've got this green length. This green length right there, that is this y value. And we've got this blue length, which is that y value. Well, what are we doing with those? We should be adding together, correct? Okay? So when I add those together, let's see if I can actually stack these here real quick. If I stack them, okay, this point right there, that point right there is the distance that is generated by taking the f of x value plus the g of x value, and it gives me that point. Okay? So that point right there is the y value that is defined by f plus g of x. So what we do then, okay, that's just for one x value, right? We're going to go and do it for an infinite number of x values to the right and an infinite number of x values to the left. And if we keep doing that, we'll be adding different y values together all the time. And what we'll generate is this purple curve right here. Does that make sense? Okay. And what I've shown, like this point right here, would correspond to probably that point right there when it's all said and done. Okay. But all we're doing is we're grabbing a y value off of the red function, grabbing a y value off the blue function, and then adding them together, and then plotting that value, okay, that y value at that x that we chose. Okay. If I was subtracting, it'd be the same thing. Okay, except for instead of adding, I would be subtracting the y values. If I was multiplying, I'd multiply the y values and so forth. Okay, so that's the visual of what it means to combine functions. Okay, and when we talk about combining functions, that is referring to adding, subtracting, multiplying, and dividing. Okay, those four operations. Does anybody have questions on that? Is that something we can do? Okay. If I were to give you, let's look at this. Let's just say we've got some function. Let's call it square root of x plus 8. And then let's say we've got another function. Let's call it negative x squared minus 3 do it this way. X minus 3 squared okay. So let's say I gave you those two functions. Okay? And I asked you to go ahead and find what f plus g looked like for the x value of, let's just get an easy x value here. Let's say an x value of 8. Okay, yeah, 8's not real good either. Let's go 1. X value 1. X value 1 would be better. If I ask you what is f plus g at an x value of 1. Well, let's rewrite what that really means. That means find f of 1 and add to it g of 1. Well, that notation to us means this. That notation means what is the y value when x equals 1 on f, which is the green curve. Okay? Well, if I look at the green curve, isn't the y value 3? Does that make sense? Okay? So f of 1 is 3. Okay? Now it says, what is the y value? It's the same thing for the red function when x is 1. So we're coming here, I'll find the y value when x is 1 on the red curve. It's down here, which is negative 6, right? What do I get when I add those together? Negative 3. So f plus g of 1 is equal to negative 3. Okay? Now, the idea then is that I should be able to plot 1, negative 3 right there. That point would be a point on f plus g of x. Okay? Now, we talked yesterday, day before, that if I want f plus g of x, what I can do is I can take the square root of x plus 8 and add to it, that's f. Now let's add to it negative x, or the opposite of x minus 3 squared minus 2. And that blue curve is the sum of these two, right? Does that make sense? That's all that is. It took the green one, pasted it right there. Okay? Took the red one, pasted it right here. Now, I did have the way I wrote it, okay, I had a plus here, but it's plus this thing that is opposite. So it just turned it into a negative. Does that make sense? Okay? So this is the sum of those two things. Okay? When we had it looking like this, wasn't that the point that we plotted? And said at that point at f plus g of 1 should be at 1, negative 3. Now you see everything else on that blue curve would be what I would get if I took f plus g of 2, f plus g of 3, f plus g of 4, and it would plot all those other points, and this is then that curve that is created. That purple or blue curve is what is generated. Is that okay with everybody? Now, here's my question. Remember, we found that f plus g of 1, f plus g of 1 ended up giving us negative 3, right? But we found that by first getting the 3 here, and that plugged in there and gave us a negative 6. Can I do the same thing by plugging in 1 right there? If I plug in 1 there, I get 1 plus 8. It'll be minus then. It'll be 1 minus 3 squared minus 2. So 1 plus 8 is 9. What's the square root of 9? 3. Okay. Now order of operations says I need to do this first. What's 1 minus 3? Negative 2. What's negative 2 squared? Positive 4. Okay. So we'll have minus 4 minus 2. What's 3 minus 4? Negative 1 minus 2, negative 3. Is that the same thing we found earlier? A different way? Okay. So we can either combine the rules and get a new rule and then run the x value through that new rule like I just did. Or we can leave the old rules, the green one and the red one alone, run our x value through the green one, get a result. Run our x value through the red one, get a result. And then do the adding, subtracting, multiplying, or dividing that they want us to do with those two results. Does that make sense? Okay. So you have alternative pathways that you can generate the same results from. That is combining functions. What I want to talk about today is a very important concept, and it's called the composition or composing functions. Okay, collectively they're called composite functions. Okay, when you guys write a paper, what's another word for, like if I'm writing an English paper, what's another word for writing an English paper? Starts with a C. Composing. Okay, we're doing the same thing here. Okay, we're composing functions. So when I compose a paper in an English class, okay, I'm putting a bunch of ideas together to create this kind of overall idea, right? Okay, to maybe substantiate like a thesis or something like that. Maybe we can think about it as taking a body paragraph, or maybe usually it's like what, 3 body paragraphs, an introduction, a conclusion. That's kind of how you first try to start learning how to write your first types of papers. But you're putting those 5 paragraphs together to formulate this overall idea that is being relayed in your paper, right? Okay, so that putting together is called composing. Okay, what we're doing here, think about like what do artists do when they write music? They call it composing, don't they? Or like especially if you're like anybody in like symphony band or anything like that, like you play compositions. Okay, it's because they've taken little things, little components of music, and they wrap them together and they create this overall piece of work. Okay, that's what we're doing here. Okay, now the notation for this can be kind of fuzzy for people. Okay, says we're going to consider these 2 functions. Actually, I'm going to go a little bit easier. Let's take these 2 functions out right now. Actually, this is fine. This should be okay. It says let's consider a very important way of combining 2 functions. Okay, and I don't really like the word I put here, combining, but this is really what we're doing. But combining should elicit the 4 operations. Composition is not an operation. It's not adding, subtracting, multiplying, or dividing. People think it's multiplication. It is 100% not multiplication. Okay, but if I've got these 2 functions, okay, it says we can create a new function by doing the following. Okay, and we write it this way. We say f of g of x. That's how we read that. F of g of x. Okay, now you kind of see like that g of x is nestled inside parentheses, right? That g of x is the innermost thing in regards to our functions here. Okay, and we can do this with multiple things. So I want to make another one here. Maybe I have like f of g of h of r of x, just getting kind of ridiculous with it. Okay, basically what you're going to do is you're going to find the function that is identified. F, G, H, and R are all functions. They're all different algebraic rules. Okay, you're going to find the one that is directly stuck with x right now. Which one up there in that green stuff is directly stuck with x? R, right? Okay, R is directly stuck with x. So that's the one you will start with. That's what we call the innermost function. Okay. Basically what's going to happen here, and I'm going to go back up to this red one, but basically what we're going to do, so G, because it's stuck to x, is our innermost function. So what we're going to do is we're going to look at what G is. G is x squared plus 1. Does that make sense? Okay, so G of x is the same, because equal sign means is, right? Or is the same as. You can phrase it that way if you want to. So because of what we know is substitution, can't I replace that with x squared plus 1? Does that make sense? So I'm going to rewrite this whole thing, but take the g of x and replace it with its algebraic equivalent. X squared plus 1. Okay. Now we get to this. Now we only have one function left over. F is the only function left over now. So what we're going to do then is we're going to go to f, okay, and this becomes the input for f, okay? So when I go to f, f is the square root of x, okay? But now, remember, your input is going to take the place, whenever we have an input, it takes the place of x in the rule. Does that make sense? So wherever I saw x in the f of x rule, that is the square root of x, I'm going to now replace it with what I have highlighted there, x squared plus 1. Okay? So that new rule, the square root of x squared plus 1, is what we call the composite function f of g of x. Okay? Now, that is the hardest way of doing it, okay, which sometimes is unavoidable, okay? They might ask us for the algebraic rule, okay? But let me show you what we're doing here visually, okay? All right, so f was x. No, f was square root of x, right? Square root of x. And g of x was equal to x squared plus 1. Okay? What is happening here? Okay? Let's think about taking, like if I wanted to know what f if we were interested in what f of g of 1 would look like. Okay? So this is the numerical approach instead of the algebraic approach. Okay? We're going to look now at the function that has x attached to it. Okay? Now when I say has x attached to it, that x is now the value 1. Does that make sense? So I'm going to look at g of 1. Okay, well, what does g of 1 mean to me? G of 1 is what? G of 1 is what? It's the y value, correct? Yeah. Okay. So if G of 1 is the y value, it's the y value when x is 1 on the g function, right? Well, the g function is the purple one. Let's go to the purple one. What's the y value? 2. Okay. So now we know g of 1 is 2. Does that make sense? So can I replace that with 2? So this is actually f of 2. So now I get this new question. What is the f of 2? What is the y value of the f curve when x is 2? It's that number right there, correct? Does that make sense? When x is 2, okay, now it's the square root of 2, or ends up being 1.414, okay? But here's the idea. So if I plot that point, okay, so what's going to happen here, so remember, what was my initial x value? My initial x value that I plugged in was 1, right? I go through this entire process of plugging 1 into g, evaluating, taking that 2 now, plugging into f and evaluating. That's the final outcome I got, right? Radical 2. I'm going to plot that point real quick. 1 comma square root of 2. It gives me that blue point right there. Okay? So here's the graphical thing that happens here. If I were to do this for every x value of 0, x value of 1, x value of 2, x value of 3, and all the x values that are in between. Okay? And plotted their results like I plotted A, what they are going to look like is the square root of x squared plus 1 is going to be that graph. Does that go through A? That make sense to everybody? Okay. GeoGebra does a nice job here because we can actually say, once we write what f and g are, we can ask it to find, I can just type in f of g of x, hit enter, and it will produce the curve that I'm looking for, produce the algebra that I'm looking for. Okay. And now what I can do here is I can plug in x to be 1. Well, if I plug x to be 1 in here, like I did in the last version, if x is 1, what's 1 squared? 1 plus 1 is 2. So when x was 1, did we get square root of 2? Yeah. Okay. So what we're doing here with these questions is that. Okay. That's called a composite function. Okay. One way of thinking about it is, we like to call. I just had a stutter and a tuck. What we like to refer to or call functions are machines. Okay. So think about this. If I were to take, let's say, I don't know if that's how you spell peeler. If I'm peeling an apple, that's how you spell peeler. Huh? An apple peeler? Okay. Is that how you spell it, or is it E-A-L? We're going to go with that. And let's say this is a masher. Okay? I like to think about my functions as machines. Okay? So my input is going to be an apple. Okay? I put it through my first machine, and I get an output. Does that make sense? So this is analogous to what we were doing earlier when I had f of g of 1. Okay? My first machine was g, and my input was 1. The first output that I would have gotten when we did this was 2. Does that make sense? That was my first output. Okay? Then that output becomes the input again for my second machine f. So then I put 2 into the square root function, and it gave me back radical 2. Okay? So I'm thinking about machines. If I put my apple in my peeler, now I get out peeled apples, right? Then I put it in my masher, what do I get out? Which is applesauce. Okay? So we started with 1, we put it through, got 2. That becomes the input now for our next machine, and it gives a final output of radical 2. Okay? That's what composite functions are. Okay? Take an initial value, put it through a machine. That becomes now the output of the first machine, but is the input of the second machine. Run it through the second machine, what's your final result? Okay? And you can do that as many times as you want. You can create as many machines or functions that you want to generate an output, a final output. Okay? You're going to see from time to time notation that looks like this. And this is where I think students get confused about whether this is multiplication or not. Okay? They see that open dot, right? You see where it says F open dot G? That open dot is notation for the word composite or composed with. Okay? So we say F composed with G of X. That notation, it's kind of old world notation. A lot of people don't like it. So what we do is we just rewrite it, and basically I start left to right, and I write down the first letter I see, and when I see composed, I put a parenthesis. And then when I see the next letter, I write the next letter down, and then I put a parenthesis, and if an X follows that second letter, I just put an X down, and now just close things off. Okay? I'd have to look at your calculator, because not all calculators have that. So if I had like F composed of G, composed of H, composed of R, like I had earlier, and then an X, the way that's going to write, you just go left to right. You see F, write F down. Okay, you see this composed with, so parenthesis. You see G, write G down. See this composed with, write another parenthesis. See this H, write H down. See this composed with, write another parenthesis. You see R, write R down. And that gets them in the right order. Does that make sense? And now R backs up with X, so I'm going to put X down. And at that point, you're really done, but we've got to close off that parenthesis. So we put that one in. And then we got to close off that parenthesis. So we put that one in. And we got to close off this first parenthesis. So we put one more. It kind of looks like a bunch of parentheses kind of get backed up there at the end, but it's because we're closing off ones that we've already opened. Okay? We're not going to get into 3 and 4 of these things. We're going to do 2 for the most part. So you're going to see F composed of G. Now, understand that this notation, okay, this notation does not equal F of X times G of X. You see the difference? How many times did I write of X here? Twice, right? Here we're not doing that. There's no X right here with this F, which means this means multiplication of the two functions. This does not mean multiplication of two functions. This is composite, okay? And I think that is one of the things that, algebraically speaking, across all of mathematics, people struggle with is the notation. I think probably the number one thing, like if I were to take all the classes that I've taught for every single year that I've taught, and we try to look at like the types of errors that are made on homeworks, on tests and quizzes and that kind of thing, the largest category of errors would be made because of notation. If we could draw like links back to why that error happened, it's usually because of notation. Okay, I know that in personal experience, the number one thing I had trouble with in a lot of my classes was notation, because textbooks don't explain it. Okay. A lot of teachers will just start using the notation and not explain it. Okay, I think there's value in that. What happens? Okay, so we were using. I just want to go back to the two functions that we were using a little bit ago. G of x was equal to x squared plus 1. So I'll write it up here. So G of x was equal to x squared plus 1. F of x was equal to radical x. Okay. So what we did initially was we took x to be 1, and we plugged it in here to this and got 2 back, right? And we took that 2 and plugged it in to this rule and got square root of 2 back, right? Okay. If we were able to create the composite function, which looked like this, if we were able to create that, then I could take this 1, plug it in here, and get directly to this. Does that make sense? You see how it lets you kind of jump this middleman here? Okay. Now, I personally think that this is only beneficial, creating this rule, if they have like x equals 1, x equals 2, x equals 3, x equals 4, and so forth. If they have like a handful of x values that you have to evaluate, I think that's the only time that this would be really useful to us. Because they only want me to do it once. Plug your x value into G, get an output. Take that output, plug it into F, and get our final result. And that's going to be the easier thing to do. Okay. So here's an example. It says let f of x be x squared and g of x be x equals 3, or x minus 3. So find the functions f composed of g and g composed of f and their domains. We'll do that, but we'll do that later. Let's do this one first. Let's do f composed of g composed of f. 5. Take a minute, take a second, and write down, notation-wise, a different way to write that. Yeah, I'm gonna open that for everybody. Yeah. Yep. So remember, this 5 is your x now, right? Okay. So if I want to rewrite this in a different format, I'm going to do it this way. I'm going to say f. I see that composed symbol, so parenthesis. Then I see g. Okay. And now because g is the last thing, I'm going to put 5 here like that and close it off. Okay. So now I look at the innermost function. The innermost function is g of 5, right? So let's figure out what g of 5 is. So basically what we've got going on here with these things is two problems at once. If we can separate the two problems and evaluate them separately, it makes the process easier. So let's just look at that right there. What is g of 5? If I come up here and put 5 in, what do I get back? 2. So this number here, g of 5, is the same thing as 2. So let's replace that green thing with 2. Now the green thing is the only thing that gets replaced. The f, we haven't addressed that, so it stays put. Okay? Say that again. So we took the g because that was the innermost function. That's the one we're going to focus on. That's why I put a box around it. And now I take 5 as the x value and see what I get when I plug it in to that function. And that gives me back 2. So now I replace g of 5 in that essentially formula or expression here. Replace that with 2. And now I got a new question, right? Now they're asking what's f of 2. I'm going to go to the function f. And wherever I see x, I'm going to plug in 2. So what do I get when I plug in 2 right here? I get 4. Okay? So f composed of g of 5 is equal to 4. Okay? Now I want to do one more. That is not here. I want to do, let's go g composed of f of 5. So when I write that, what did I do compared to what we did in red? I just reversed the order, right? So now if I rewrite it, it's g composed with, so parenthesis, f, and I've run out of functions, so now I'm going to put the 5 there. So now what do I do first? I'm going to go to the what function? I'm going to go to the g function or the f function? I'm going to go to the f function, and what am I going to plug into the f function? That tells you what to plug in, right? Okay, so we go to the f function, I'm going to plug in 5. What do I get when I plug in 5 right there? 25, right? So now I'm going to replace this thing here with what it was equal to. It was equal to 25. Now it says find g of 25. Just come up here, find the g function. Where you see x, you put in 25. What do you get when you do that? 22, right? So now I'm going to ask this question. Does the order that I compose functions matter? Are those two things equal? No, they're different. Here we're seeing one's 4, one's 22, right? So they're different, okay? So what I want us to understand is that composite functions are not, okay? And when I say this, I'm not saying that it couldn't happen. I'm just saying in generalities, it is not a universal truth, okay? But composite functions are not, okay, now here's my question. I want you to give me the mathematical word. If I take 2 times 3, I get 6, right? If I take 3 times 2, I get 6, right? If I take 2 plus 3, I get 5. Take 3 plus 2, I get 5, right? I'm adding and multiplying those things, but I'm just changing the order, correct? What operation says I can change the order in addition and multiplication, but still get the same result? Commutative. Okay? So are we not asking here? Are we asking right here, using the same things but changing position? Do I get the same result? So we're saying here, basically, when I did this, I was trying to get us to recognize that composite functions are not commutative. You cannot just flip things around in any order and still get the same result. Does that make sense? Okay. So that is dealing with composite functions. I don't care right now about finding their domains. I really don't care too much about finding their algebraic composite function like we did at the beginning. I want you to be able to take 5, plug it into G, get an output, plug that output into F, and get a final outcome. Okay. I will extend, I think it was 6.6. I'll extend that beyond, I'll probably do tomorrow night.